we are going to continue our study of spacetime algebra in this lesson, and we've made really good progress. We began section 3.6 in our last lesson, and we completed, I guess, about half of 3.6.1. We talked about the spacetime split for bivectors, but we have not talked about the spacetime split for vectors yet, I don't think, and we certainly haven't spoken about the cross product. So hopefully today we'll get started up to 3.62. All right, so let's begin. Actually, we're going to begin with 3.61 because we did finish the generic material earlier, and we've already talked about the spacetime split for bivectors, right? We talked about dividing the bivectors into the group sigma I0 and then sigma ij, where neither I or j is 0. And we realized that this group we're going to take to be the dual of the first group. There are 3 vectors here, there are 3 vectors here for a total of 6, and that is the spacetime split. So, for bivectors. But that's clearly, I guess maybe I got a bit ahead of myself, so let's see how they do it here. In terms of this relative 3-vector basis, the bivector takes the simple form. So then they give us this form. They call it F. Your bivector is F. And you can see here that these first 3 parts of the basis are sigma 1. I'm going to skip the vector mark on top. Sigma 2 and sigma 3. This is sigma 3, this is sigma 2, and that is sigma 1. And so that counts as the relative, this is a relative 3-vector. So this is a general bivector, right? This is a general bivector. And the reason you can see it's a general bivector is its basis is clearly gamma 1, 0, gamma 2, 0, 3, 0, 3, 2, 1, 3. That's a full set of basis vectors. So this is a general bivector. But we are splitting it into these 2 parts. The part that we're going to give coefficients called E, and that part will be a relative 3-vector, right? This is a relative 3-vector right here. And this is what's left, which we haven't really given a name to, right? We've given a name to a relative 3-vector, but we haven't given a name to what's left. But of course, what's left is just the dual of a relative 3-vector, right? So that's the dual of a relative 3-vector. And interestingly, they've labeled the coefficients of the relative 3 vectors with the letter E and its dual with the letter B. And they've given this whole bivector the letter F. And this is all foreshadowing, right? They're foreshadowing the fact that the electromagnetic field is going to be represented as a general bivector. That general bivector is going to be called F. And then they're showing that the relative 3-vector part is going to be related to the magnetic field. And the dual of the relative 3-vector part is going to be related to the magnetic field. So, I'm sorry, this will be the electric field part, and this will be the magnetic field part. So the electric field, you can see, is already anticipated to be a relative 3-vector, right? But the magnetic field is not a relative 3-vector, or the magnetic field part, if you believe this foreshadowing, it's the dual of a relative 3-vector. So that'll be interesting, but it's not going to stay that way for long, as you'll see in a second. The next line says what I just said, that F involves a relative 3-vector, which is this stuff right here, right, a relative 3-vector, and the dual of a relative 3-vector, which is this guy here. Now notice that last dual part suddenly looks like this. So now, if we write it in this final form, right, the dual of a relative 3-vector, we need to write B as a relative 3-vector. And that's what they do here. They say the magnetic field is given by this relative 3-vector. The dual of the electric field is given by this relative 3-vector. The dual of the magnetic field is, well, here's the duality. It's on the right. So B itself, the magnetic field itself, this magnetic field vector has to be a relative 3-vector. So this is the relative 3 vector that goes right here, and then here's this thing that turns it into its dual. So this is a little bit of a language, I want to say trick, but it's not really a trick. It's very straight. It's completely straightforward, but we have to decide what we want to call the magnetic field and where we want to call it the magnetic field. First of all, this is all notation here, right? This is a general bivector, and any general bivector can be broken up into a relative 3 vector part and the dual of a relative 3 vector part, right? So that's what they're trying to say here. But I'm going to use the word electric and magnetic field because when we start applying this to electromagnetism, which is the promise of this paper, then we'll see that these names are appropriate, meaning calling this the electric field and this the magnetic field. The problem is that what do we call this relative 3 vector here that represents the magnetic field? Because the dual of the relative 3 vector is actually what is the magnetic field, right? If the magnetic field itself was truly a relative 3 vector, then it would kind of be part of this, right? So the magnetic field part has got to be this piece here, which is the dual of a relative 3 vector. And yet we're creating a relative 3 vector right here for the magnetic field, and we're going to say, oh, Bi, its dual is Bi. So the way this works is, well, we got to make contact with basic physics. And in basic physics, the magnetic field is a vector just like the electric field. There's no distinction between the magnetic field and the electric field in elementary physics, except for the fact that the magnetic field is understood to be an axial vector, and the electric field is understood to be a polar vector. So they are different, but there's no symbol in elementary physics to say that, right? Like we don't have some little thing that says, oh, this is like we could do this. Like we could have written, oh, the magnetic field is a vector, but it's an axial vector, so we give it a dot. The electric field is a vector, but it's a polar vector, so we give it an open circle, right? So that's how we distinguish these two types of vectors. But that's not what we do, right? We just call them both vectors, and we just try to keep track of how they transform if we ever even need to, right? Because usually we're defining the magnetic field through a cross product, and that cross product should automatically take care of the direction of the magnetic field. And likewise, the electric field is not defined through a cross product. So given that, we consider them both to be regular vectors in three-dimensional space. And that's exactly what's going on here. This is a relative 3 vector, which we learned in the last lesson is supposed to represent a regular vector in three-dimensional space. And as long as we consider these sigmas, these relative 3 basis vectors, the sigmas, to treat them just like regular unit vectors for three-dimensional space. So that's what we've done here. We take the magnetic field and we give it regular 3 vector status, but we just remember that when we define the electromagnetic field multivector, the bivector for the electromagnetic field, we've got to take the dual of that thing. And once we take the dual of that thing, of course, riding along with the I is the axial quality that is restored to this vector. Okay, so enough about that. Unlike the canonical decomposition 3.28, splitting the bivector into dual relative pieces in this manner requires the specification of a particular time-like vector gamma 0 in the basis 3.39, which spoils the frame independence of each relative piece. So that's important. So we got to have a quick look at reminder of 3.28 and 3.39, although they're pretty obvious when we see them. So what they're getting at here is that any bivector F can be written in 2 different ways, well, at least 2 different ways, right? The first is this canonical way that we've discussed extensively. And there was no reference in this to coordinate systems. This is a very, very general way of writing bivector, it has a canonical part with a known signature. I think we defined it as a known negative signature, and it has this phase part. I is perfectly defined for any coordinate system. I is always going to be the product of the basis vectors of the grade 1 portion of the space, and phi will never change regardless of what basis system you're in. But F can also be written as a partition between a relative 3-vector part, all right? We could call this a relative 3-vector part, and the dual of a relative 3-vector part. So it's a relative 3-vector dual part, right? Like that. And I guess just to make it clear, I'll put that there. And the point is, this does matter a lot. This matters on very carefully which gamma 0 you choose. And if you switch to a new gamma 0 prime, you better understand this switch relationship, because these guys are going to definitely change. And so this partitioning into these two pieces is going to fluctuate depending on what basis you choose and the relationship between the bases that you choose. So that's the point they're trying to make there, is that this is basis dependent and this is not basis dependent. Okay, so let's move on. So what they're saying is the specification of a particular time-like vector in the basis which spoils the frame independence of each relative piece, right? Well, that's actually true for, you can change any of the vectors and you'll screw it up. But in particular, yes, the time-like vector is even more sensitive because the definition of sigma is really wrapped up in the time-like part. Only the total bivector F produced in the sum is a proper geometric object. Right? So when you unravel F into this form, and you put this whole thing together as one bundle and you call it F, well, F is the proper geometric object. And that's true of any multivector, right? If you cast the multivector in a basis, these coefficients are going to change whenever you change bases. But this object itself, if you handle it like you do on the left-hand side, that won't change. But this will, right? Because what you'll actually end up seeing is if you change these vectors enough, stuff that lived in the E will now live in the B, right? And that makes perfect sense if you understand the relativistic transformation of electromagnetic fields, right? You know that electric fields manifest as magnetic fields in moving reference frames. So that makes perfect sense. But this object here is, this totality of this is the true, they call it the geometric object, in the sense that you can do geometric algebra, geometric products, you can do geometric operations on F, and you never have to refer to coordinates at all. They're invariants in all coordinate systems. Many of the things are invariant, right? The components are not invariant when you switch coordinate systems. But, it's an important element of physics. What are the aspects of F itself which are invariant? Now, F is a geometric object, but the things that would be invariant would be, say, the total energy stored in the magnetic field. That would be, or total amount of energy radiated by an object. All these things have got to ultimately end up being reference frame independent. And if it's not reference frame independent, physics just says it's not an important quantity in a truly physical sense, right? It could still be important and interesting, but it's not necessarily, it is necessarily an important quantity if it is invariant under these kinds of transformations, these basis transformations. We choose the suggestive labels E and B to anticipate their correspondence to the electromagnetic field vectors in section 5, but we can already see at this stage the inevitable equivalence in form of F, the bivector F, to the Riemann-Silberstein complex vector given in 1.1. So we didn't bother, you may remember early on when we started this, we didn't read the first section, which was sort of the history of mathematical formalisms for electromagnetism. What the paper wants to point out, fairly, right, as far as I know, is that geometric algebra is sort of the culmination of a long history of different mathematical formalisms of electromagnetism, and they cited a whole bunch. One of them was the Riemann-Silberstein complex vector. So somewhere in this, there was the Riemann-Silberstein complex vector presentation of electromagnetism. So there's a history of trying to find the simplest form of the electromagnetic field equations and the simplest structures to call the electric and magnetic fields. And so at some point, somebody did create something that looked a lot like this, but it wasn't integrated into a geometric algebra. So they're showing again how these formalisms are all people desperately, the way that I think they're trying to express this is each of these formalisms are people trying to get to they want something simple and beautiful like geometric algebra, but they don't see geometric algebra. What they see is different elements of how electromagnetism works. And they were always able to make a formalism that worked, but there's some complication to it. There's some ability to simplify and integrate it. And now we think we've got it. We think geometric algebra actually is that final formalism, right? So in chapter 1, they set that up. They set up that idea, and we kind of skipped chapter 1. Okay, as with the complex canonical form of a bivector, that was this thing. That was F equals F e to the I, e to the capital I, the way we're doing it, phi, right? With the complex canonical form of a bivector, the existence of this complex spacetime split is not at all apparent when working solely with the real components in the magnetic field tensor. Well, I definitely understand that this thing here is hard to understand in terms of tensor analysis. Not sure that I'm going to immediately agree with this, right? Because we know, I know that I can write down the electromagnetic field tensor like this, and this has to be done in a certain frame, right? These are tensor components, right? Each of these guys are tensor components in a specific frame, right? So you can't actually produce this matrix unless you're in a specific reference frame. And, if you look at it, it kind of cleanly breaks up into something that's obviously not vector-like. It's anti-symmetric tensor-like. And the electric field is sort of out here. So it's not like it's completely invisible in this tensor form that you can break things up into this split here, right? I mean, this split here, to me, those are, they're clearly related. And I've always thought of it in terms of this way, and I always knew, the magnetic field is weirder than the electric field, so it has this strange structure inside the electromagnetic field tensor. So the complex spacetime split is not at all apparent. I mean, I feel like this is a split, right? This is a spacetime split in the regular tensor form. So I certainly agree with the first part. The complex canonical form of a bivector is not obvious in tensor analysis. But the spacetime split, I kind of feel like it is, actually, to be honest. But regardless, the point is that even if I feel like it is visible, clearly this is simpler, right? This is definitely easier to assemble and put together, right? It's just two vectors and the pseudoscalar for the algebra. So it's certainly easier to write this down than that whole box that I actually had to pause recording to write down. Okay, so let's move on. All right, so briefly, we note that the product between a vector and a bivector that we defined in section 3.1. So this is hard to read out loud because they repeat the word that, right? See, these are annoying things that you don't get when you... Briefly, we note that the product between a vector and a bivector that we defined in section 3.1. First of all, you should never use that. If in all of your writing, never use that. I'm going to write this down. If you find the word that in your text, rewrite the sentence so it's not even there. And here's an example. Look how much better this sentence is, right? Get rid of this, get rid of briefly we note that, and just start with the product between a vector and a bivector as defined in section 3.1, comma, can be used to compute the spacetime split. So I've reduced the number of words, and the clarity has gone up a lot, and you don't have those annoying that's in there. Anyway, proceeding. So we're trying to compute the spacetime split. So we have an arbitrary bivector f, and then we note this obvious fact that bivector f times gamma 0 inverse, there's no change here. But we also note that for gamma 0, it is its own inverse, because gamma 0 squared is 1, right? We've been doing that where all the others have a square to minus 1. So then we execute the associativity here, right? We associate these two, and we compute that to be, we compute this associated spacetime product. We got rid of that, right? And that is going to be f dot gamma 0 plus f wedge gamma 0, right? And then this whole thing is multiplied by gamma 0, right? That gamma 0 goes to there, and you end up with this expression, right? And with that expression, the point is I can take f. If I'm curious, if I have an arbitrary bivector f, and I want to know what are, and I'm in this, and I'd like to know what is the spacetime split, this expression here represents the relative three-vector part, and this expression here represents the dual of the relative three-vector part. So this will ultimately be the part we call E, and this is the part we call BI, right? And that split itself isn't too hard to understand. It's worth looking at, though. So here I've repeated everything, right? I've written it all down in this form, and we're at this part. So we're just going to look inside the parentheses. The text obviously has the gamma 0 there, and then another gamma 0 there, and it distributes it through, but we're not going to distribute it through right now. So let's just look at this contraction part. Well, if you have the full bivector, you have E, say you're looking at the E1 gamma 1 0 part, and you contract it with gamma 0, which is what the instruction says. So anything that is in this relative bivector part, because remember that's sigma 1, right? That's what that is. So anything that's a relative, one of the relative bivector basis vectors, well, that's going to look like this thing here. But we know how to multiply a wedge product. We know how to contract a wedge product against a vector. And you end up with contracting these two to get 1, so you get gamma 1. And then you contract these two with a relative minus sign, because you had to flip the order of the wedge product. But then you have gamma 1 dot gamma 0, which is 0. So this part goes away, so you're left with gamma 1. So this term here clearly picked out the sigma 1 and returned gamma 1, which doesn't seem, but that's not a relative vector, right? Our claim is it's got to be a relative vector, but then we remember we have this gamma 1 hanging out there, that's got to come in. So, or this gamma 0 hanging out here, that's got to come in. So this becomes gamma 1, gamma 0, which is gamma 1, 0, which is in fact sigma 1. So clearly, as long as you have a relative bivector as your base, as long as you're dealing with the component that is a relative bivector, this expression is going to pull it out, or I should say, this expression is going to pull it out with the gamma 0 included. And likewise, you can go through the analysis over here, right? Over here, right? Well, I guess I should show that it eliminates these other ones, right? It's really not hard to see, right? All the terms that have all the components that are in this basis, that have basis vectors that are dual to the relative three vectors, right? Like, for example, this one. Well, when you contract it with gamma 0, you're going to get an expression that looks like gamma 3 wedge gamma 2 contracted to gamma 0. And again, our formula always serves us well. It's gamma 3 times gamma 2 dot gamma 0 minus gamma 2 times gamma 3 dot gamma 0, but these products are always 0. So any term that's living inside of the subspace that's dual to sigma 1, sigma 2, and sigma 3, right? All those the dual vectors to those guys, when you contract with gamma 0 in this first term, they're going to go away. So the only thing that's going to be left is the relative 3-vector part of F. So if I ever have a general bivector, let's see, I'll write a general bivector G, say, if I want to know, hey, what is the relative vector part of G? Well, I say, oh, that's easy. I just do G dot, what's the formula? G dot gamma 0, right? G dot gamma 0 times gamma 0. And what's left over after that operation is the relative 3-vector part of G. Actually, we're going to do this quite a bit in some examples that we do soon. So we're just getting used to it. So now the question is well, what about this part? This is supposed to pick out, wait a minute, did I say relative? Yeah, this is going to be the dual to the relative 3-vector part. There's no word for that. There needs to be a word for this guy. I guess I could call this sort of the polar part and the axial part. Would that work? I'll have to think about it. But anyway, this is the dual to the relative 3-vector part. And you can see that if you are, so this whole expression is just two examples of the components. This is F written out in all of its components with some dots in there. But look at this one component that lives in the relative 3-vector, the dual to the relative 3-vector part of F, and it's supposed to be wedged with gamma 0, right? Well, it'll survive that wedging because being in the relative part, it doesn't have a gamma 0 inside its definition, so it'll survive the wedging. But right away you see that all the parts that are in the relative 3-vector part, they do have a gamma 0 in there. So if you change this to a wedge product, right, that would equal 0. So it immediately eliminates. So this process right here, this wedge process right here, immediately eliminates the relative 3-vector part right off the top. So the only things that can survive are the relative, the relative 3-vectors dual parts. So, for example, this one survives, and you end up with a trivector, but then you geometric multiply again by gamma 0. Well, the inflation part of that multiplication, because you're multiplying by a vector, so you have one inflation piece and one contraction piece. And that inflation piece is obviously 0 because you've forced gamma 0 in there already, and now you're inflating with gamma 0. So the inflation part goes away. So what's left? Well, the contraction part is left. But the contraction, the first contraction, will give you gamma 0 dot gamma 0, gamma 3 wedge gamma 2 left over. But all the other contractions are going to be gamma 2 dot gamma 0 and gamma 3 dot gamma 0, which are 0. So the only thing left is this. So we now can say that the dual to the relative 3-vector part for any vector G, right, we can say that's going to be G wedge gamma 0, gamma 0. So that's what they're saying in that paragraph, that if you wanted to pick out the relative vector part or the dual to the relative vector part, you use these two formulas to do it. The first term, i.e. lowers the grade of F, it contracts F to a vector perpendicular to gamma 0, that's what contraction does, and then multiplies by gamma 0 to produce the relative 3-vector basis, right, which we just demonstrated. The second term inflates or raises the grade of F to a trivector including gamma 0, right? We demonstrated that too. That's this process right here, right? A trivector including gamma 0, that's what that thing is. And then contracts out the gamma 0 part, right? Then you do a contraction, which looks like a geometric product here, but it's just a contraction because the inflation part is 0, is guaranteed to be 0. So that's nice. And it leaves behind just the dual basis. So we demonstrated all that. Okay. So, all right. right, so that's looking good. Let's move on to the next paragraph. Similarly, we can now revisit the cross product between two bivectors defined in section 3.52 as the dual of the commutator bracket. I don't want to go all English teacher on this, so I'm going to just ignore how annoying that sentence is. But we should go back to 3.52 and see what they're talking about. The dual of the commutator bracket is defined as this cross product. So let's check that out real quick. And that is right here. Oh yeah, I remember this. Right, so we define the commutator bracket as 1/2 of the commutator. So in this world, this commutator bracket carries around this this commutator symbol carries around this 1/2, which is not the way it's done in physics, right? In regular quantum mechanics, for example, this commutator is literally just the commutator. But they did define this bivector cross product, and they say for completeness here. Yeah, that's why we kind of blew through it. They defined it because they're going to use it later, but they just wanted to point out that since they had already defined this commutator bracket, which is the grade 2 part of the geometric product, right? So that's why it was useful. And we actually used this a couple times since then. So by defining this geometric product, this difference of geometric products, that pulls out the grade 2 part of the geometric product of two arbitrary bivectors. I think we used this when we wanted to show that the grade 2 part of the geometric product of a bivector with itself, right, was 0, right, because this commutator, obviously, for A and A minus A and A, it equals 0. So you're able to show that the geometric product, or the geometric products of a bivector with itself, only has a grade, well, it can't have a grade 4 part. This shows that the grade 2 part goes away, so it's automatically a grade 0 part. I think we just did that a couple lessons ago. But anyway, they had already defined this commutator bracket in the paper, so they said, but before we go, we're going to define something later on called the cross product between two bivectors, right? We're going to give it that same familiar symbol. So now all of a sudden we have this weird thing called the cross product, and it's just the commutator bracket, but it is the Hodge dual of the commutator bracket. So I guess this might be a hint about our minus sign. Apparently we're saying this. We're saying, given a multivector, multiplying on the right, that's its dual, right? I think what they're trying to say is that the Hodge dual of this product, of the Hodge dual of M, is actually defined this way, right? I should really go through this and just, go back to the actual definition of the Hodge dual in straight up exterior algebra and make a link here. But clearly they're calling this the Hodge dual, and they haven't introduced the new duality we're working on now, so there's no redundancy, there's no ambiguity. So I think what's going on. This is the Hodge dual, and the regular dual is just without the minus sign, I suppose. That's what I'm supposing. But regardless, it really doesn't matter what we call it. I'll try to work on those definitions later. But they are defining this bivector cross product as the commutator between the two bivectors, right, multiplied by the inverse pseudoscalar, right? And they didn't apply it, but they then said, after we introduce the relative three vectors, it will become clear that this product is completely equivalent to the traditional three-vector cross product, which is why they're choosing this notation. So that's what we're now should be expecting. If we had remembered this, we'd be all excited. So now returning to the actual statement, the bivector cross product defined in this way, they're saying that if we compute that bivector cross product for our three relative bivector basis vectors, we will get these expressions here, which are cross products obeying the right-hand rule. 1 curled into 2 gives you 3, 2 curled into 3 gives you 1, 3 curled into 1 gives you 2. So I guess we could go ahead and test that out. It might be worth testing out. Let's just test out one of them. Let's just test out the first one. So let's just brute force check this out, right? We have sigma 1 cross product sigma 2. So here's the definition, right? Here's the commutator. We got the factor of a half and I inverse. So I'm just going to blow this whole thing up, right? The inverse of the pseudoscalar is minus the pseudoscalar. So I inverse equals minus I. So because of that, I will pull out a minus sign in front with the 1/2, and then I'll just have an I over here. Whoops, I've already kind of commuted that I in here, right? This part here is I, right? This part here is I, this part here is I. So I've actually brought it in. This part here is sigma 1, this part here is sigma 2, this part here is sigma 2, and this part here is sigma 1. So I've actually already expanded everything. Now you just have to carefully contract this all out, but of course all you need to know is that they anti-commute. Each of these things anti-commute. You got this sigma 0 piece in here, and that just squares to 1, so we can immediately just like eliminate that. And then when you do eliminate that, I think I did this step by step. You eliminate that and you end up with 1, 0, 2, 1, 2, 3. And then the idea is we anti-commute this 2 and the 1, so you end up with this 2 squared. That anti-commutation introduces this sign. The sign goes away because when you square gamma 2, you get -1, so you're left with gamma 1, gamma 0, gamma 1, gamma 3. And then you commute this one, pick up a minus sign, you get gamma 1 squared, which is another -1. So you get plus gamma 0, 3. So this whole thing reduces to gamma 0, 3, which you can see is the reverse of a relative basis vector, right? It's a bivector with a gamma 0 argument. And then you do the same thing over here, and you end up with the exact same expression. So you end up with -1/2, 2 times gamma 0, 3, and the 2's cancel, and then you flip the 0 and the 3 to eliminate the minus sign, you get gamma 3, 0, which, I guess, as the final coup de grace, I should write as sigma 3, right? So it's sigma 1 cross sigma 2 equals sigma 3. So we've basically found, and you check this for the other combinations, and you basically realize that we have defined, in the world of Gibbsian Heaviside vector analysis, the cross product between two basis vectors is well understood. And these guys, as promised, mimic that behavior under an appropriate definition. So now we have an appropriate definition of the cross product of two of these relative basis vectors, and this is all space-time algebra stuff over here, right? This is all space-time geometric products. So we've defined yet another product in terms of a bunch of geometric products. And the reason we do this is because we're trying to show that all of our math that we've done in the past exists in the formalism of geometric algebra. So that's kind of fun. That's totally cool. These are precisely the defining relations for the familiar relative three-vector cross product, which motivates its standard notation. That's why they're notating it this way. Thus, the bivector cross product forms a closed, non-associative Gibbs subalgebra for the relative three vectors that is entirely embedded within the space-time algebra in a natural way. Right, so what they're trying to say here is actually kind of important. To be clear, everything the paper says is important. It's because it's a very dense knowledge paper. So that's why we're going through so carefully, because each sentence is actually full of important meaning. But here's our space-time algebra, right? This is the basis system of the space-time algebra. We have the four basis vectors, but now we're going to write down the bivector basis as these relative three vectors and their duals, but this is still the bivector basis. I mean, this is literally the basis we've been doing before, right? Gamma 1, 0, gamma 2, 0, gamma 3, 0, gamma 3, 2, gamma 1, 3, and gamma 1, 2, I think, if I get it right. Or gamma 2, 1. No, gamma 1, 2. And so, and then these are the trivectors here, and then this is the pseudoscalar. So this is the same same spacetime algebra with a slightly different notational organization. But now what they're saying is, okay, we know that this thing is closed under the geometric product. I can take any multivector, and multiply it by any other multivector, and I'll get yet another multivector. So this whole algebra is an algebra. You know, it's defined by this metric. It's also defined by this pseudoscalar, right, which we've chosen to be right-handed, right? So, you know, it's defined by the pseudoscalar, defined by the metric here, and it's and the geometric product is the product that elevates it from a vector space to an algebra. So we got that, but here's what we've just discovered, right? We discovered that we can define, using this geometric product, another product called the cross product, but it's very limited in terms of the geometric algebra. You can't take this cross product and put any multivector on the left and any multivector on the right, at least the way we've defined it, because we've defined it in such a way that it requires two bivectors, right? The geometric product commutator of two bivectors, right? And we take the dual and then the opposite of the dual, right? If I put that minus sign out in front and get rid of that inverse, it's 1/2 of the commutator between two bivectors, the dual of that, and you take the negative. You multiply it all by -1. But anyway, regardless of how, you know, how obscure the definition might be or not, we've defined this cross product. It's just not a very useful product for the overall algebra because it doesn't work for most things in the algebra. But it does work for bivectors. But more importantly, if you focus on that thing for just these three bivectors, right? If you just take those three and you formulate sigma 1 cross sigma 2 and sigma 2 cross sigma 3 and sigma 3 cross sigma 1. And then you understand, of course, that sigma I cross sigma j equals minus sigma j cross sigma I, which is evident from the commutator part of the definition. What you realize is that whenever you take the cross product inside these sigmas, you always get another one of these sigmas out. You don't get one of the duals out. You certainly don't get one of these other vectors or scalars out. You get another bivector, but specifically, you get a bivector only in this segment of the algebra, which basically says, you know, if you look at that and you think about that, if you have a bivector that's just part of that algebra, call it E, right? And you add to E another bivector that's just another relative bivector, say you added, E2, right, together, you'll get another relative bivector. I guess that's the way to say it. If you take two relative 3 vectors and add them together, you get a relative 3 vector, right? You never leave this basis space if everything you're adding together comes from just these 3 basis vectors. So that's interesting. So that means, and is there a 0 vector here? Well, yeah, of course. If you have 0 sigma 1 plus 0 sigma 2 plus 0 sigma 3, well, you've got a 0. So you've got a 0, and you certainly have negative, right? Because, you can definitely define minus E1 plus E1 equals your 0 vector, right? And this is, again, a relative vector, and 0 is also a relative 3 vector. I say relative vector, but I mean relative 3 vectors, which are bivectors, right? So I keep emphasizing that. It's bivectors as far as our whole algebras are concerned, but we're treating them like their own little 3 vectors now. So the point is this guy here is clearly a vector space, right? You have negative vectors, you have the 0 vector, and you have this definition of addition between vectors, right? So it's definitely a vector space. But now with the introduction of the cross product between these guys, and noticing that this is completely closed, right? With this cross product, I now have an algebra. So this guy here is actually an algebra when you add in, when you include the notion of a cross product. So this is now a subalgebra in a sense, right? It's not strictly speaking a subalgebra, because for this to be a subalgebra straight up, it would have to be a subalgebra under the straight geometric product, and it's sigma 1, sigma 3, the geometric product of sigma 1 and sigma 3. The geometric product of this, you take a minus sign, you get a 1, you get a 1, 3. Yeah, it's going to leave the this collection and move over into the dual side, right? Because you're going to end up with a minus sigma 1, 3, I think, right? Which is going to be over here somewhere, right? So you don't really have a subalgebra for the whole algebra, because it's not closed under the geometric product. But it is an algebra under this cross product, right? It is an algebra under this cross product. And the way they actually say it, they say the bivector cross product forms a closed, non-associative Gibbs subalgebra for the relative three vectors that is entirely embedded within the spacetime algebra in a natural way. Well, it's definitely an algebra that's embedded within the spacetime algebra. There's no doubt about that. Subalgebra, I don't know. I just went through this whole thing about why it's not, strictly speaking, a subalgebra. Because the technical use of subalgebra is you need to have the same product. It's not really a subalgebra. So I'm going to quibble over the word subalgebra there. Anyway, moving on. But the point is, the thing you need to understand is that it is an algebra, right? We have created a new algebra just for these relative three vectors. And it's non-associative. Why is it non-associative? I guess we should address that, because if A is a how would we write this? If E1 is a relative three vector, cross E2 is a relative three vector, cross E3 is a relative three vector, it's famous that the cross product is not associative, right? The green and red calculation order will give you different answers. So it's non-associative, right? Which is fine. I mean, it's funny that the Clifford algebra is so rich and yet it's associative, which you think would make it simpler. But it's a very, very rich subject, interestingly enough. So no word left behind. So we've got the words associate, non-associative we've taken care of. We've got this problem with the notion of subalgebra, because I just don't think that's appropriate. I just don't think that's appropriate. But it's definitely, it is a non-associative algebra that is embedded within the space-time algebra in a natural way. That's definitely acceptable. Hence, all the standard manipulation with the vector cross products still apply to the relative three vectors in the space-time algebra. Moreover, the conceptual meaning of the cross product is enriched since it is induced by the more general associative product of the space-time algebra. Well, fair enough. I guess there is the problem that if we did, say, 4-dimensional or 5-dimensional space-time, that cross product would be bivector products that might have higher dimensional components to them. I guess I'm waiting. What I'm struggling with here is I'm waiting to benefit from this extra conceptual meaning. I certainly understand how the cross product picked up this definition and how the definition works and why it creates this embedded subalgebra. I don't suddenly feel like I understand the cross product in some new and better way due to this, but hey, it's definitely just fascinating enough just as it is. So that's all great. Okay, so the next section is on paravectors. Very nice. Now, basically, obviously, what we're going to do is we're going to reorganize how we define a general multivector, and we're going to use some new plan on how to do that. And we will pick up right here the next time we meet. So I'll see you next time.